Okay, so we have been going through different details regarding single particle dynamics in Stokes flow and also looking at aspects of fluid inertia, aspects of particle inertia, and before we move further on, which is going to trying to understand particle interactions and how particle interactions become important, there are few points which we want to actually mention by completing the entire story of particle dynamics in for a single particle dynamics. So, what we have been seeing so far is, if I were to imagine that there was a phase space which was spanned by, let us say, Reynolds and Stokes, and a large part of what we have done focuses at the origin of these two axes. So, Stokesian suspension that we have looked at focuses on the origin of this intersection. As you move along Reynolds number, you are basically looking at problems where effects of fluid inertia is important. So, what kind of scenarios would be when fluid inertia starts to become important? How does fluid inertia become important in first place? So, Reynolds, if you did not know anything else, you could define Reynolds using this. There is some characteristic velocity of the object, there is a characteristic size, and then characteristic density of the fluid and viscosity of the fluid. So, if you were to say that I am actually moving along the Reynolds axis, what kind of fluids or what kind of systems would you encounter as Reynolds becomes larger? What is it that you would think of that has a larger Reynolds number? So, you can have an object that basically is larger, I mean has a higher velocity. So, the velocity, as we know, can be due to its own settling motion, could be due to an imposed flow. So, one way to think of is that you are basically looking at particles that are bigger in size, right. You are effectively thinking of objects that are actually moving with the size being basically becoming larger and larger. Now, how do we increase the velocity? If you think of your settling velocity or even a rise velocity, we have only said settling so far. Right, this is the expression of either settling or rise. If delta rho is positive, then you have delta rho is what? Delta rho is particle density by minus fluid density. So, if it is positive, then it is settling. If it is negative, then it is rising motion. So, when would the settling velocity become large? Obviously, with size, that goes without saying. Anything else? So, one way to play around with the settling or rise velocity is play around with the density ratio or the density contrast, right. You have delta rho is rho p minus rho f. So, one way to have rho p minus rho f is if you imagine that you are looking at systems where the particle has significantly higher density than the fluid. Now, if you do that, what would say, if you take a characteristic example of, let us say, water drops in air. So, for water droplets in air, what is delta rho by mu? I mean, keeping everything else fixed. Numerator would be approximately 1000. We are going to work with rough numbers. What is mu? Mu is mu of air, right. So, mu of air is SI units 10 to the power minus 5. So, this would be meter square per second. So, this is around 10 to the power 8 meter square per second, right. This is just to get a ballpark number of what is that prefactor multiplying, because obviously we are not playing with g here. So, the only thing then you are left with play with is the size. This to tell you how u is actually changing in the problem. Now, if you have the other scenario of bubbles rising in water, what would be delta rho by mu? Now, rho p is close to 1, it is a gas bubble. Rho f is water, so it is close to 1000. So, delta rho is negative 1000, right. So, you have magnitude is close to 1000. What is mu? What would be the case of mu? This is mu of water, which is 10 to the minus 3, SI units 10 to the minus 3. So, this is around 10 to the power 6 meter square per second. Now, if you do, let us say a sand particle falling inside water. So, let me write this: water droplets settling in air. So, if I write u as 2 by 9 some constant g by a square, where this constant c is delta rho by mu. So, I am trying to actually get a feel for what this constant is in different kinds of system. So, this has units of kinematic viscosity. So, this would be 10 to the power 8 meter square per second for water droplets settling in air. For gas bubbles rising in water, so it is typically what you would see when you pour a glass of cold drinks, there would be bubbles which would be rising up. So, this is approximately 10 to the power 6 meter square per second. What would be let us say mud or sand particles settling in water? What is delta rho? Delta rho is, I mean, at max maybe 1000. Sand's density compared to water will not be a lot. If you have a metal particle, then maybe you can have it twice as heavy as water, but if you have a sand particle, then it would be, the difference between the two densities would be few hundred, correct, few hundred kg per meter cube. If you think of sand, the density of sand, I mean, how heavy could sand actually be? So, if you have roughly, so I will just take this to be around 10 square, around few hundreds, and viscosity of water is, right. So, this is approximately around 10 to the power 5, if not smaller. I have taken a pretty large contrast, 10% density by which it is heavier than water. So, that is around 10 to the power 5 meter square per second. So, what you can see very quickly from this, that if you were to consider a same size particle in these three scenarios, the chances of you achieving higher Reynolds number in the gravitational settling problem is obviously highest in the case of water droplets in air. Then even for the case of bubbles, it tends to get higher quite soon. So, this kind of a regime that you are looking at, there will be a lot of problems, and one of the cases where Reynolds number is actually fairly high is the scenario which is known as bubbly flows. Again, bubbly flow is something that you all would have seen. You take a glass, you take a bottle of cold drink, pour it into a glass, and then automatically you see a lot of gas bubbles which are rising up spontaneously. So, that kind of a scenario, there is a chance that you would actually be operating at a reasonably large Reynolds number scenario. Stokesian suspension, if I now move along the axis of Stokes number being large, that is, how did we define our Stokes number? We defined our Stokes number as a ratio of time scales. So, there was a particle relaxation time scale which we encountered at the end of last class by the flow time scale. So, the particle relaxation time scale, how was it defined? It was the mass of the particle by the drag coefficient or the resistance of the particle, right. That is how we started, and then there is a flow time scale. and then when you use 2 by 9, if I am ignoring the buoyancy effect, then rho p a square g by mu. There will not be any g, this is just the mass. Yeah. G tau p is u. So, u is actually g times tau p. So, that is your relaxation time scale divided by a flow time scale. So, what happens as the particle density or particle size increases? Stokes number will keep on increasing. So, if you go for bigger and bigger particles, you are effectively going for scenarios where inertia is increasing and Stokes number is increasing. So, a large Stokes number problem would effectively typically be problems which are like granular flows, dusty flows, flows where you are looking at big sand particles that are actually moving. So, a size is large compared to the ambient air medium, density is also large. So, you have a large Stokes number scenario. If the flow, so flow time scale could be anything, it could be whatever you are imposing. So, it could be related to the shear rate, the inverse of the shear rate that is there. So, keeping the flow time scale fixed, if you were to go for bigger and bigger particle or heavier particle, you are effectively increasing your Stokes number. You are holding it fixed. So, the flow time scale is something that is imposed. So, imagine that you are doing a problem of a shear flow, right. So, this shear flow has a shear rate which is given by the plate velocity by the gap. Now, in this particular problem, you basically start looking at the behavior of particles whose size are continuously being increased, keeping everything else fixed. As the particle size increases, you are automatically going for a higher Stokes problem. And this boundary is going to be a boundary which is where you are looking at particle density and fluid density being comparable. Because what is your Reynolds number? Reynolds number is viscous time scale by flow time scale, right. What is viscous time scale? Viscous time scale is a square by nu or rho fluid a square by mu fluid tau f. What is Stokes number? There is obviously a factor that I have written down, but rho p a square mu fluid tau f. So, if you take a ratio of the two, you are going to get that Stokes by Reynolds is going to be rho p by rho f. So, this line is basically the line of systems which are neutrally buoyant. Where particle density and fluid density are roughly equal. So, we are trying to create a phase diagram of what is actually going on in the Reynolds Stokes plane. Now, I will come to the vertical axis. I have also drawn a vertical axis here. I will come to the vertical axis, but before that we need to actually see. So, we have bubbly flows in the large Reynolds number limit, we have granular flows in the large Stokes number limit. We have a scenario which is when you are looking at Stokesian suspension, which is the origin, and you can see that bubbly flows are going to come here, because as you are moving towards this axis, you are effectively going towards Stokes being 0. When does Stokes become very small and Reynolds become very large? See, the Reynolds axis is when Stokes is negligible, the particle inertia is negligible, but fluid inertia is increasing. So, as I said, the ratio of Stokes number to Reynolds number is the density ratio, particle to fluid density. So, when would you have a scenario where Stokes is negligible, but fluid inertia becomes very high? So, negligible Stokes, but Reynolds is very large is going to happen when the fluid density is much larger than particle density, and that is the reason why I said it is bubbly flows. Similarly, along this axis, Stokes is very large, but Reynolds is negligible. And when is that going to happen? When particle density is significantly larger than fluid density. That is the reason why I said granular flows, dusty flows, where you have air as a medium and then you are looking at particles which are 1000 times heavier, water drops in air. So, in those cases you will first hit Stokes number becoming large and then you will encounter Reynolds becoming larger. So, first you will have a large Stokes problem before you have a large Reynolds problem. Is this picture clear? Is this diagram clear? So, before we move along the z axis, we need to discuss a little bit more regarding what is the consequence of Reynolds basically being non-zero and also Stokes being non-zero independently. So, along those two axes. So, if I first focus on Stokes being non-zero, I will not discuss Reynolds first, I will discuss first Stokes. So, these are particles which are known as inertial particles. Now, we have spent extensive amount of time discussing about the modeling of a second law for particle motion with all the forces that are acting. Now, in today's class, to discuss this, I am going to go for the simplest of all that model. The simplest model is basically saying that mass times particle acceleration is equal to Stokes drag. This should be plus. The drag force due to the particle motion is responsible for mass times acceleration. Now, you might say, is this the appropriate equation because I had added mass, I had history term, etc. Now, all those other terms, if you go back to your added mass, what was the added mass term like? The added mass term was like mass of the fluid times something like the particle acceleration minus the fluid acceleration, right? So, when you take a ratio, if you remember when we did this exercise, when you take a ratio and divide throughout by the mass of the particle, terms like added mass are going to depend on density ratio. Similarly, terms like history force will also have density ratio dependence, which means if you are looking at very inertial particles, large Stokes number particles or heavy particles, if I am looking at heavy inertial particle means that particle density is much larger than fluid density, I can ignore all the other forces and just model this as a balance between Stokes drag and the acceleration of the particle. Other terms can be ignored. So, it is a very simple model. You do not even need to say it is Maxey-Riley or Bassett-Boussinesq, etc. You are just saying mass times acceleration is equal to a linear drag, that is all, and that is actually an accurate description, because now if you go back to your Maxey-Riley-Gatignol equation and if you do this non-dimensionalization consistently, you will see that the added mass term goes as density of the fluid by density of particle. There is a factor which is the density ratio or inverse density ratio. If you define your density ratio as rho p by rho f, then it will be the inverse of it. It depends on how you are defining it. Similarly, the history term that you had in the equation, the history term, if you remember, was 6 pi mu a square root pi nu, and then there was an integral, right. Now, here if you once again divide by the mass, you have mu a square mass root nu. Now, what is mu a by what is this quantity? if you look at this, the mass of the particle mu a divided by the mass of the particle will give you a particle relaxation time, correct. So, this term that you are going to get will have a tau p, and then there will be a root nu term that is going to appear here. If you do the non-dimensionalization for that equation for the history term, there will be a tau p which will come in because it is a viscous term, but there will also be the kinematic viscosity that is going to be present in that term. So, when you are going to write that particular term, there will be a term which will appear here that would be something like 1 by square root density ratio, that is going to appear in this equation. So, the summary of all that I am trying to say here is, if you have heavy inertial particles, you can ignore effects of added mass and history. So, water drops in air, sand particles in air, in these scenarios you do not need to actually bother a lot when you are thinking of particle dynamics at low Reynolds number. Obviously, like if you are doing very large Reynolds number, where Reynolds number based on the particle is around 100, then the picture is completely different. But I am saying at low Reynolds number, compared to a sand particle in water and a water drop in air, in the first case history is important, added mass is important, whereas when you are doing a 10 micron droplet in air or you are doing a 20 micron sand particle moving around in air, you do not need to take into account added mass or history effects. Whereas if you do exactly the same setting in a water environment, you are looking at sediment transport, you are looking at a 50 micron microplastic being transported by waves in the ocean. It is not really appropriate if you say that in that particular scenario you should not be accounting for all the other forces, because density ratio is very close to 1. So, that is the argument behind taking this very simplified model. Now, jumping on to what we wanted to actually do here, that if I write down the equation is going to be u infinity minus u bar by tau p. Okay. Now, if I non-dimensionalize this equation, so I non-dimensionalize this equation by saying that there is a length scale, let us say the particle, I choose a characteristic length scale L, and there is a time scale which is tau f. Okay. So, there is a length scale and then there is a time scale, which means you can construct a velocity scale which would be L tau f, right. So, if I write this, I have L tau f, for time I will have by tau f. So, then sorry, this is L by tau f, velocity would be length by time. So, that is L by tau f, and then time is tau f. So, this is all non-dimensional. Similarly, u infinity is L by tau f, u infinity star minus L by tau f, u by tau p. Okay. So, if I write down the non-dimensional equation, I have the non-dimensional version of my force balance is L by tau f into 1 by tau p into tau f square by L into u infinity star minus u. This is just a non-dimensional version of this equation, choosing some characteristic length scale and characteristic time scale. Now, L and L are going to cancel out tau f, and so finally I land up with a term here which is tau f by tau p. What is tau f by tau p? It is inverse of Stokes number. Okay. So, then this equation is u infinity non-dimensional, u bar non-dimensional by Stokes number. Now, if Stokes goes to 0, What kind of a system do we have in mind? Stokes is tau p by tau f, right? If Stokes goes to 0, what kind of a system are we thinking of? Tau p is significantly smaller than tau f, which means the particle loses its momentum rapidly compared to the time it takes for the flow to change or the flow time scale. You imagine you are doing a shearing problem, there is a shear rate that is there, right? Now if you ask that there is a fluid parcel basically being transported over a distance of particle size, how much time does it take? That time is going to be the particle size square, a square, sorry, it would be, time would be gamma dot inverse. That is the time it takes for, based on that fluid parcel, to move. Now if you are comparing how much time it takes for this parcel of fluid or this particle actually to lose all its momentum, whatever was its initial momentum that you have imparted, that would be tau p. So tau p being much smaller than tau f effectively means the particle inertia is negligible. We are back in that origin. We are looking at Stokesian suspension. And so if you are not thinking of, so when Stokes is negligible, then so the governing equation that you have is du star dt is u infinity star minus u bar star by Stokes. So for very small Stokes, your particle velocity is equal to the fluid velocity evaluated at its center. Now, when the fluid is static, then obviously the particle is going to come to rest. If there is nothing, so if the fluid was static, then you just have du dt star minus u star by Stokes. This will have a solution which u star of t is u star of 0 exponential of minus t by Stokes. So it is going to lose all its momentum. How rapidly does it lose its momentum? That depends on the value of Stokes number. If Stokes was actually very small, then you can see that exponential will very sharply go to 0, right. If Stokes was a very small number, then it is exponential, negative exponential of a very large quantity times t. So it goes to 0 rapidly. So it will lose all its momentum and come to a static state if there was no background flow. But if there is a background flow, it is going to faithfully follow the background flow. This is u infinity at the particle center. Now you all know that this is obviously an approximation because there is going to be a fraction term, etc., all that will be there. But right now we are basically ignoring all those fraction corrections. We are saying that if there was negligible particle inertia, the particle is going to just latch on to the fluid and move like a tracer particle. It will follow streamlines. So if I draw streamlines, so I'll draw few streamlines pattern. So this is a streamline pattern which is given by a velocity field which is ux is equal to minus omega y, uy is equal to plus omega x. It is an anti-clockwise rigid body rotation. You can draw a problem where I am just drawing some very simple linear flow fields that you have already seen before. Ux equals alpha x, uy equals minus alpha y. So this is again a planar extensional flow. Now if you add a particle here in these problems, if Stokes was 0, the particle is just going to follow the streamlines. It will not do anything else. That is the Stokes approaching 0 limit, where it is behaving exactly as an inertialess particle and ignoring a fraction correction. Inertialess particle means it moves like a tracer particle. Okay. The interesting part comes when you say Stokes is small, it is not 0. So, what will happen if Stokes is small? So, the way to do this is do it in a more formal manner, where you say that the particle velocity can be written in a perturbation series. There are corrections I am posing. If you remember this exercise, we have also tried when we were trying to account for fluid inertia and we failed there, but this is the first thing that you do when you are doing any problem where there is a small parameter. You say, okay, I know the solution when that small parameter is identically 0. So, let me try to see if I slightly change that parameter and give it a non-zero value, how much would the solution change. This is the essence of what is known as a regular perturbation approach. So, what this does is if you if you substitute this for the left hand side, it is going to be ddt of u naught Stokes plus u1, and then there are terms which I am not writing down explicitly, which are order Stokes square term. On the right hand side, you have u infinity. I am dropping the asterisk here because it's all are non-dimensional. So, I am not separately writing down asterisk terms. And then here you have u naught plus Stokes u1 plus order Stokes square divided by Stokes. So, this becomes ddt of u naught plus Stokes of ddt u1, and then there is an order Stokes square term. On the right hand side, I am going to have u infinity minus u naught, and what I will do here, I am going to multiply throughout by Stokes. So, so that I do not need to carry it in the denominator. So, then this is Stokes u1, and then there is an order Stokes square term. Now, what is the next thing that we do in this kind of an exercise? After we do this kind of a perturbation, what is the next part of our calculation? We match coefficients or terms which are with coefficients of the small parameter, which is Stokes here. So, that is called collecting terms in orders of Stokes. So, you first check what is the 0th order of Stokes equation. So, when the LHS, there are no term which is 0th order in Stokes. For the RHS, you have u naught and u infinity being equal to each other, which comes back to what we already knew before, and I am putting now the label that this is at a particle position, that the particle moves with a velocity which is equal to the fluid velocity at its center of mass. At order Stokes, the left hand side has an equation which is du naught dt, I mean ddt of u naught. I ignore the Stokes square term, obviously this is balanced, here I get minus Stokes u1. So, my expression is u1 is equal to minus ddt of u naught. Okay. Now, what is u naught? U naught is the background velocity evaluated at the particle center. So, this is minus ddt u infinity xp. Now, once again go back and refresh what we discussed towards the end of last lecture. What is this ddt? It is a material derivative, but what kind of a rate of change is it measuring? It is measuring along a particle trajectory. So, ddt is actually dou dou t plus u dot del. So, it is a slightly bothersome term. It is a rate of change of the fluid acceleration as measured along a particle trajectory. Slightly, I mean, not a very nice term, because you are taking fluid velocity and measuring its rate of change along a particle trajectory. But then we are in luck here, because we are doing all of this perturbatively, which means this d dt term that I have here, that is dou t plus u naught del, I should also be expanding this. I should be writing this as u naught plus Stokes u1 plus order Stokes squared term, and then so the advective term in the equation u dot del, where u was the particle velocity, now is written as advection in that series form. So that d dt is now turning out to be dou t plus u naught dot del plus Stokes u1 dot del, and then there are order Stokes square term. Now what is u naught? It is the background. So this becomes dou t plus u infinity dot del, right, and then there are order Stokes term. So the purpose of doing all of this is d dt is now going to be capital D dt plus order Stokes, where capital D dt is the material derivative as measured along a fluid streamline, which is something that is now convenient, because now we can write u1, because u1 is strictly a correction that is order Stokes. So when we are writing this minus d dt there, we should be writing it as minus capital D dt of u infinity, because this has a part which is capital D dt and then there is an order Stokes term. I shouldn't be carrying that order Stokes term there. So the final summary of this exercise is that the particle velocity, which is written as u naught plus Stokes u1 by solving that heavy inertial particle equation, turns out to be u infinity minus Stokes d dt of u infinity, and then there are order Stokes square term. What is this term? Material derivative of this is the fluid acceleration, right. So what you are saying here is that when inertia is small but non-zero, there is a correction to the particle velocity. When I am doing this approximation, there is a correction to particle velocity which depends on the local fluid acceleration, because all of these are evaluated at the particle center. So as it is trying to move, so now the question is, as it is trying to move here, it cannot move along a streamline. As it is moving along a streamline, it is experiencing a correction that depends on the acceleration. So as you see these problems, the rigid body rotation, sorry, this motion is, yeah, it is trying to move this way, counterclockwise. So as it is trying to move in these either rigid body rotation or a planar extension, is the acceleration 0 or non-zero in these problems? It is a steady flow field. 0 acceleration, non-zero acceleration, if this is my u infinity. So you will have a term in your acceleration, if you write down your acceleration in Cartesian coordinate, that would be ux dou x, and then for a steady problem, what is the other term? it's u dot del u's x component, right. So then uy dou ux dou y, and similarly the y component of acceleration is going to be ux dou uy dou x, uy dou uy dou y. So now you go back to your problems. For the rigid body rotation, is any acceleration 0, non-zero? What is ax infinity? The first term is 0, right? Ux doesn't depend on x, ux depends on y, and uy is obviously there. So ax infinity is going to be omega x and then minus omega. So this is minus omega square x. For a rigid body rotation, the x component of acceleration at any point is going to come from the term uy dou y of ux. So if you plug in that value, you are going to get uy is omega x and minus omega is dou y of ux. What is ay infinity? So ux is minus omega y and dou x of uy is plus omega. The second term is 0. So this one is 0 and this one is 0 for a rigid body rotation. So at every point as this guy tries to move, it is experiencing an acceleration which is minus omega square x and minus omega square y. That is the acceleration. So you choose this particular point. This is in the first quadrant. So the direction of the fluid acceleration at this particular point is going to be in which direction? There is a minus, right? So the direction of acceleration is towards the center. Now the correction to the velocity is u infinity minus Stokes acceleration, which means the particle is going to experience a force in which direction? Going outward. So when it is actually moving in this vortex, at every point it is experiencing a correction to its velocity that wants it to go outward. So with that small Stokes correction, the particle is going to get centrifuged outwards. Now for this flow field, if you repeat that exercise of ax infinity, there is going to be only the first term ux dou x which is plus alpha, and there will be the second term which will be uy dou y which will also be plus alpha, right. When you do it for a planar extensional flow, the acceleration is always positive, which means at any point there is an acceleration which is in this direction, there is an acceleration which is in this direction, which means what is the correction to the particle velocity? It will move inward, it will go towards the stagnation point. So here as it tries to move, it is going to move inward. It will go and collect towards the stagnation point. So this is a profound difference that you are starting to observe due to particle inertia, that with this small Stokes behavior, what you are observing is that if you are looking at heavy particles, when particles are heavy, they tend to actually get ejected from vertical regions and they tend to get pulled towards stagnation points. So
this is all happening due to the presence of like a very small Stokes number.
yes, so this is the first effect of Stokes number. I mean obviously what we are trying to do here is we are writing all of these things down when Stokes is negligible. So now if you see if you treat this as a velocity field, this is the particle velocity field, this can be written as divergence of u infinity minus Stokes of divergence of a infinity. Now, what is divergence of u infinity? It's 0, because the flow field is incompressible. Minus Stokes divergence of a infinity, I can write it as dou t of u infinity plus u infinity dot del u infinity. So, divergence of the particle velocity field, divergence of dou u infinity dou t can be written as dou t of divergence of u infinity, which is equal to 0. So, this becomes minus Stokes, and now I will switch to tensor notation, dou xi of u infinity j dou u I infinity dou x j. Now, if I take the dou xi inside, this is going to become dou u j infinity dou xi dou u I infinity dou xj plus uj infinity dou square ui infinity dou xj dou xi. What is this term? 0, because this term is u dot del divergence of u. Okay, that term is 0. Here I have a term which is now minus Stokes dou uj infinity dou xi, which if I write in terms of symmetric antisymmetric part, this is going to be rji infinity plus s, we are using e, right, ej infinity, and the second term is rij infinity plus eij infinity. So, the first term is rji infinity rij infinity, the next term is rji infinity eij infinity eji infinity rij infinity plus eji infinity eij infinity. Okay, all good? What is this term? Should be 0. Again, tensors are your friends and you use them appropriately here and it reduces your work, right. So, now what you have here, it is minus Stokes. Okay. Now, rji infinity can be written as minus rij infinity rij infinity, okay, and the other term that I have there is eij infinity eij infinity. So, this term divergence of the particle velocity can be written as minus Stokes E square minus R square or plus Stokes R square minus E square. R square is the magnitude of the rotation tensor, E square basically again being the square of the magnitude of the standard tensor. So, what does this say? When this is positive, then it is a source, particles are getting ejected, right. A region in the flow where this is actually positive is acting like a source of particle. A region in the flow where this quantity is negative, this is acting like a sink, and the region where it is positive is dominated by vorticity. A region where this quantity is negative, it is strain dominated. So, why am I going through all of this? Because the example that we took where we did this exactly was a very simple rigid body rotation and a planar extension. What is E in rigid body rotation? 0. What is R in planar extension? 0. So, we took some very simple examples, but now if you take a big leap and you do, let us say, a fully turbulent flow, homogeneous isotropic turbulence as just an example, and you have heavy inertial particles in this particular problem. So, you put particles in this and they are moving according to the equation that du dt of the particle is equal to u infinity minus or u fluid minus u by Stokes number, the equation of motion for heavy inertial particle. So, what you are going to observe, at least when Stokes is not really very large, that particles are going to get ejected and they will arrange themselves in regions which are strain dominated. So, even though the flow is highly unsteady, it has a lot of stochasticity in it, you are going to observe that particles are going to come and collect themselves. They are not going to be uniformly distributed. There will be what is known as preferential concentration or clustering of particles. So, when you do an arbitrary inhomogeneous flow where everything is varying temporally and spatially, if you want to get signatures that where particles are going to go and collect, where would you find a higher density of particles, because the particle, if you think of its velocity field, that is not divergence free. If you define a field, which means there are enough particles to think of a continuum quantity for the particle velocity, that field is not divergence free, they are going to form clusters. So, even though the underlying flow field is incompressible, particles are going to preferentially sample. A tracer particle does not preferentially sample. If you have a tracer particle on a streamline, it will stay on that streamline, if you imagine a steady problem. Whereas an inertial particle, if it lands on a streamline, it can get ejected away from the streamline depending on whether that streamline is part of a vortical region or straining region. The direction of ejection or the direction of migration depends on whether you are in a strain dominated or a vorticity dominated region. So, broadly what we have done here, we have started from a very simple model for the particle, taking the Maxi-Rayleigh-Gattignol and then saying, okay, like we are looking at heavy particles. So, the evolution equation is very simple, and what we have concluded here, that when you are looking at a very complicated 3-dimensional flow field, if you were to actually inspect the sign of this quantity, because for the flow field that is a scalar quantity, right. So, you inspect and you find out that which parts of the region, which patches of the region are more vertical than the rest. You will start getting clues where particles are going to cluster, and this is quite important. This is important, let us say if you are trying to think in terms of, in a turbulent problem, you have droplets of fuel which needs to combust. So, now you are thinking these droplets are in a medium which is significantly lighter, so they are heavy particles. So, they are going to go and arrange themselves in regions which are strain dominated. So, they are going to preferentially be located there. So, when you look for the next thing, which could be their combustion, which could be their coalescence, if you want these droplets to collide and grow, if you are interested in these kind of questions, you have to acknowledge the fact that these are heavy particles, they are inertial in nature. So, they are not going to be present uniformly in the flow field. They will have a certain non-uniformity in their distribution, and why is it non-uniform is something that you can understand from a very simple argument based on this force model. Obviously, all of these things get more involved and detailed when you think of effects of added mass, history, etc. But for the simple case of heavy particles, if Stokes number was not negligible, was not 0, but it was small, you can argue this. Now, obviously, if you take Stokes and you make it larger and larger, this kind of an approach, whatever I have written down here, this is strictly valid when Stokes is very small. Something of this sort is only going to be applicable when Stokes is a very small number. When Stokes becomes order 1, this kind of an approach does not work, and it does not work for primary one simple reason, that the solutions of this particular equation that we have for order 1 Stokes starts to show a lot of peculiarities which are otherwise not present when you are thinking of that particles are just going to follow the tracer with a correction to the local fluid acceleration. So, for higher Stokes number, there are a lot of other things which will come up that will not be captured by this perturbative expansion. You cannot do this in this perturbative manner. Okay. So, this is basically the summary of what is going on in Stokes. In the next lecture, I will touch upon what will go on with Reynolds, and then I will conclude about the Z axis. So, this kind of gives you a comprehensive picture when you are trying to think in terms of single particle dynamics. Now, everything we are doing here is primarily focusing on spherical particle, but a large part of this discussion also carries on for particles that are non-spherical. Obviously, if it is non-spherical, you have to keep in mind about particle orientation. That is an additional thing that you need to focus about, but broadly the ideas of preferential concentration, the ideas that particles effectively are going to sample regions which are more vertical, more straining than vertical, these ideas carry on. They do not necessarily change by a lot. Obviously, you have to track for the orientation part. Okay.